Good morning, class. I hope that exam 2 went well. If not, please reach out to me and we can schedule an appointment to look over your exam. Now we will begin section 6.1, Introduction to the Normal Distribution. So let's think about this for a second. What is the difference between the given two probability statements? Assume that 5 cards are selected with replacement out of a well-shuffled deck. What is the probability of getting exactly 2 hearts? And what is the probability that a randomly chosen giant pumpkin weighs more than the prize-winning pumpkin at the state fair? The first probability represents a count, i.e., a discrete random variable. And this is exactly what we discussed in section 5.1. Whereas the second probability represents a continuous random variable. So remember from chapter 1 that continuous data are data that can take on any value in a given interval and are usually measurements. So continuous random variables are ones that take infinite number of possible values. So if we look back at the statement, what is the probability that a randomly chosen giant pumpkin weighs more than the prize-winning pumpkin? So just for the sake of this problem, let's say 1,039 pounds at the Indiana State Fair. We can define our random variable x to be the weight in pounds of a randomly chosen giant pumpkin. And notice that this is a continuous random variable since it's a measurement. Weight is a measurement. Using this, we want to find the probability that the randomly chosen pumpkin, so we're going to denote that by x, the weight, is greater than 1,039 pounds. Now, another question, how do we go about listing all of the possible weights for the pumpkin since weights are classified as continuous data? To answer this question, we define continuous probability distributions using methods other than a table as we have seen in section 5.1. A density curve, also called a density function, is a graphical representation of the relative frequency distribution of a continuous random variable. They come in many different shapes and sizes. So here are a couple. We have already discussed a particular density curve, the bell-shaped curve. This was back in chapter 3. We saw in section 3.2, using the empirical rule, how the data is distributed below the curve, right? Remember that the highest point corresponding on the number line represents the mean. And then if we go 1 standard deviation, we contain 68% of the data. 2 standard deviations, we contain 95% of the data. And if we go 3 standard deviations, we get almost all of the data. We will utilize this idea for the remainder of the course. A normal distribution is a continuous probability distribution for a continuous random variable, again we'll denote by x, defined completely by its mean and standard deviation. That is a bell-shaped curve. This curve has the following properties. So 1, it is symmetric about its mean, and again we label as mu. 2, the total area under the curve equals 1. 3, the probability that the random variable is less than or equal to a value is equal to the area under the curve to the left of that value. Similarly, for number 4, the probability that the random variable is greater than or equal to the value is the same as the area under the curve to the right of that value. And finally, 5, the probability that the random variable x is between 2 values is equivalent to the area under the curve between the 2 values. Let's look at an example. Suppose we want to know the probability that a randomly chosen giant pumpkin weighs more than the prize-winning pumpkin at the Indiana State Fair. Remember that this pumpkin weighs 1,039 pounds. Furthermore, suppose we know the weights of pumpkins are approximately normally distributed with a mean of 1,038.5 pounds and a standard deviation of 0.72. To solve this problem, we first use the fact that the weights are approximately normally distributed. Therefore, we can draw our bell-shaped curve centered about its mean of 1,038.5 pounds. So here is our distribution, and the highest point gives us the value at 1,038.5, so it's between 1,038 and 1,039. And remember that sigma tells us how stretched out it is, and we'll talk a little bit more about this in a second. Since we want to find the probability that the weight of a randomly chosen pumpkin is greater than 1,039 pounds, we can mark a dotted line along the value of 1,039 and shade everything to the right. So notice I've marked 1,039 here, and I've shaded everything to the right of that value. This area is equivalent to this probability.